Alrighty, we want to take a quick look here at plane mirror reflections. Okay, plane here meaning these are a flat mirror, so this isn't concave or convex. And we're going to look at how those mirrors reflect light. So one of the things that we have to kind of get rid of in advance here, I guess, is the idea of light. Is it a particle or is it a wave? Throughout history, there's been debates. Some scientists, like Newton, were convinced that light was composed of particles. He called them corpuscles. Other scientists, like Huygens, thought that light was more like a wave. In this unit, we're going to explore the properties that verified that light behaved like a wave. Our next unit, then, we're going to start looking at some of the ways in which light can actually behave more like a particle. And then just to mess you all up, how matter itself can actually behave in wave-like matter. But that's coming up. First thing here, we can talk about the law of reflection. So if we imagine a ray of light coming towards a plane or a flat mirror, here's our incoming ray. One of the things that you should understand, this incoming ray, we call it formally an incident ray. It hits the mirror, wow, that was a nice straight line, at the point of incidence. And when it bounces off the mirror, we call it the reflected ray. We measure the law of reflection not between the ray and the mirror, so not whatever this angle is, but rather this angle here between the ray and what we call the normal. Now the normal, just like normal force, is calculated at 90 degrees away from the surface. The normal in this angle, in this case, is simply a imaginary line sprouting up 90 degrees from our plane mirror right at the points of incidence. And when we talk about the law of reflection, we basically say that the angle of incidence is equal to the angle of reflection. But we always do measure them with respect to the normal. All right, so now this is true for both waves and for particles. Right, so we can do this with a wave of whatever type. We could also do this with a pool ball. Now we can mess things up with a pool ball if we put spin on it or something like that, or if there's an imperfection in the edge where we're bouncing it off of, things like that, right? But in general, even with particles, angle of incidence is equal to angle of reflection. So this is one of the types of questions that could mess you up. Not because the question itself actually is hard, but because, what's going on here? There we go. So the question itself here is not hard, but what we've got going on here is a little bit challenging. So if we've got this angle, or this light angle, coming in, and it's going to be 24 degrees with respect to the mirror surface. What actually is our angle of incidence? Because remember, we have to calculate our angle of incidence not from the surface, but from the normal. So if this is 24 degrees, the angle of incidence then is actually going to be 90 minus 24. And what we're looking at there is 66 degrees. So our actual angle of incidence, so theta I, is equal to 90 minus 24, or 66 degrees. All right. And what that tells us as well then is that our angle of reflection is going to be the same. Right, so if I draw in my pretend I'm able to do this fairly accurately. The one that I actually care about here is my angle of reflection, theta r, which is going to equal 66 degrees as well. All right. Now, in this particular situation, yes, this angle down here is going to be 24 degrees. But be very careful. 24 degrees with respect to the mirror surface. Angle of reflection is always with respect to the normal. Okay, here's how we kind of go about doing it. If you want to see it step by step, it's in your notes then. All right. Now, this one's a little bit more challenging. So let's take a look at it. Basically, this is a big math kind of a problem. We're dealing with lots of triangles. So we're going to sketch in our normal line. And again, this 60 degrees is with respect to the mirror. And it's also, I hope it's obvious, that it's not to scale. Which means this is going to be 30 degrees. So my angle of incidence is 30 degrees, which means my angle of reflection is also 30 degrees. Trying to draw it so it sort of looks like it should here. Now, I'm going to be honest with you, there's a big problem coming in just a minute when I start to label this thing. Because this 60 degrees is obviously not to scale. I hope it's obvious that it's not to scale. That also tells me that, well, this is definitely not 30 degrees, which means this down here is not 60 degrees, but we got to deal with it. 60 plus 100 is going to be 160, which tells me that this is supposed to be 20 degrees. Right? So I'm basically here using just some basic trig facts that if I go from mirror A to my normal, that's 90 degrees. My normal down to the reflected ray off of mirror A, that's got to be the same, right? Theta I A is going to equal theta R A. And then we come down to finally where it hits mirror B. All right. If this angle down here is 20, that means this one here has to add up with 20 to give me 90, so this is going to be 70 degrees. As soon as I say that, oh, well, this is my theta I for angle of incidence onto B, which means, of course, or hopefully, of course, all right, and get this guy in there. Something like that. Angle, so theta IB is here, 70 degrees, which is going to be the same as theta RB, which has got to be also 70 degrees. So what's my angle of reflection off of B? It should be 70 degrees. Let's take a look. Okay, so we've drawing the reflected rays in. Another quick way to look at the same thing. Right, so the angle of incidence off of surface B is measured with respect to the normal. Notice that I didn't here mark in the normal here, and that this is 30 and this is 30. Totally fine to do that here, unless I'm telling you you need to include the normal. It is symmetrical, so the 60 and 60 here are fine. But over here, yes, I can say this is 20 and this is 20, but the question is asking for the angle of reflection. All right. So here's the next bit is, if we want to understand how we see images in plane mirrors, we need to understand how light comes from objects. We consider a point source of light. Light is going to radiate from that point in all directions. When we see the object, the eye receives a cone of light from the point source. The brain knows that the object is located where the rays of light converge, or where they come together. Now, let's consider how we see an image of this object in a plane mirror. So obviously, hopefully obviously, our object is sending light in all directions, but we're only really going to care about a few of those directions. And that's going to be the places where the light comes from the object and bounces to either edge of the eye. All right, so it will be a cone of light bouncing off the mirror that will make it into the eye. Now, the brain believes that light travels in straight lines and that the object is located where the reflected rays will converge. So the brain is being fooled, and the brain sees the object in behind the mirror. The rays of light never reach the other side of the mirror. Okay, they are stopped. They're being reflected, but these lights are called virtual lines. We draw virtual lines as dotted lines. Since the diagram is symmetrical, the distance to the image from the mirror is the same as the distance to the object. So what we notice is that if this object is a meter away from the mirror, it is going to appear to be a meter behind the mirror. So if we're talking about a plane mirror, we got to figure out what's going on. Well, the image in a plane mirror, assuming the plane mirror isn't like deformed and distorted and things like that, it is the same size as the object. It is vertically upright, but it is laterally inverted. which means if I hold my right hand up in front of a mirror, the left hand of the image is going to be raised. The image in the mirror is virtual, which means it's not real. This is going to become important later on. And the image is located the same distance from the mirror as the object. All right, so here could be something. We've got this. This is not a light ray here. This is a weird looking arrow. And we want to sketch the object as it would appear in the mirror. Now, how are we going to do that? Well, if I have to be really picky about this, what I'm going to do, I'm going to measure this distance. Come on. There we go. So 4.6 centimeters, which means on the other side, no, I should actually have that as a solid line because this is a on the other side of the mirror, dotted line this time. That particular point is 4.6 centimeters on the other side. All right, I also pick this point here. Oops, come on. All right, that point's important, 2.1 centimeters away. And this one up here is also important. We'll get that one in a minute. Oops, come on. And finally, my arrowhead here is give or take 6.2 centimeters away. There we go. Zoom distance here, 6.1 I believe it was. And now it's a matter of connecting these. Again with a dotted line, and we'll do a different color just to show. So in green, there is my image of the object. It's virtual, size, its actual size. It is upright, and it is virtual. Okay, so it's identical in size, upright, and virtual. Those are the ways that when we describe the object in a mirror, that's what we got to say. All right, so we find the distances to the mirror for each of the key points. The image is located the same distances on the other side of the mirror. Since the image is a dotted line, we sketch it as a dotted line since it is a virtual image. It's not formed by real rays. All right, so it's the same size, it's vertically upright, laterally inverted, and it is virtual. And that's where we stop tonight. Have fun. Thank you.